Now, this is really Fourier series now. So let me recap. What basically happens is if we have a function of time and it's periodic, so if we have some x of t here and it's periodic, I'm using this just to demonstrate. Something like this. The period is the time over which it repeats itself. So this is be the period t. The fundamental frequency f naught is 1 over t. Omega naught is 2 pi f naught, or 2 pi over t. This is all things that have been said before, so you don't have to write it. And when we have this, the value, the average value, C0, is 1 over t, the integral from 0 to t, of x of t dt. It's the average value of the function. Those are things you can just take one look at most of this stuff and calculate. It's not hard at all. Now, after that, we can say, it's not permanent. We can say that x of t here is equal to the summation from n equals minus infinity to infinity of c of n e to the j n omega naught t, and the value of Cn can be calculated as 1 over t, the integral. It can go from any point to any point plus the period t of x of t times e to the minus j n omega naught t dt. And the reason we're doing this is we're getting values of C of n that will give us in a second the actual power at each individual frequency if we square the value of C of n. I'm going to do something right here. I'm going to show you a trick to calculating this value right here. How many did the homework? Or looked at? If you looked at, did you all look at the homework? Right. Wasn't it up there? Can't hear you. What?
Maybe just had the op-amp ones.
Was there stuff on Fourier too added?
No.
Just the op-amps up here? Thank you for telling me. All right, well, I'm going to show you the trick now. Here's the real problem. This x of t here is defined from this point to this point as just t, right? Isn't it just some constant? If this has a value a, right? Then the slope of this here, really, call this tau. If this is tau right here, and that's the period t, the slope of this would be, the actual slope would be a over tau, correct, class? Now, if you have that, that means this equation for this line right here would be a over tau t, only between 0 and tau, correct? And the function's 0 from then on. Now here's the trouble with that. Well, to do this integration, that's going to be t times that constant a over tau, right? T times e to the minus, effectively at dt. That's an integration by parts, right? If I know one thing about integration by parts, is students generally foul those things up. It causes them difficulty. They don't like doing it. Mainly because there's ways to make mistakes there because it's a little more intricate. You have to be very, very careful. Well, I'm going to show you a way where you don't have to do that most of the time. And I think you should have a vested interest in this. Because if we want to calculate C of n, and I apologize for those at home not showing up, or me not putting them there. The problem is, I may not have put that homework there. I think. But you got the op-amp homework, so you're done with the op-amp homework, right? Were there any last questions about op-amps before I move into this area? I should have asked that. Most of the stuff we covered, didn't we do a pretty good job? And if honestly, how many did the op-amp homework? Wasn't it pretty clear about how to do it? Was there any questions at all? It shouldn't have been hard at all. It should have been just smooth because it's just circuit analysis with, instead of 1 over j omega c, it's simply what? 1 over sc, right? And the inductor instead of j omega L is just simply SL, right? and then the op-amp loss. No voltage across the input, no current into it. That's it. That's the whole game in that one. So it's fairly easy. This is a little more difficult. This is what I started with, didn't I? Now, using this function right here to represent x of t here means integration by parts. I bet you, if you're honest, you'll admit to this. How many don't like integration by parts? Me neither. It's like convolution. I hate that too. But I have to do it and I have to understand. So the way to circumvent that, in most cases we deal with, not all, is not evaluating that integral, but doing something, it's a trick called the derivative method. Are you with me on this? I'm going to show you the derivative method in order to calculate C of n that goes there without ever doing the integration. So I want you to make sure you start a clean section. I just want to put this up here, but now I'm going to do something, and I'm going to show you exactly what I'm doing and why I'm doing it. Hopefully you can appreciate this. So now, I'm going to come over here and say that if this is t, and this is x of t, I know I'm going to start out with a simple function, like this. That's pretty good. It's a pretty good approximation to a square well, or square wave, right? For your, your JK flip-flops and stuff like this. It's going to have an amplitude A. This will be tau, and this will be period t. And you can see it repeats itself. Y'all agree? Now that itself has, we can calculate what C of n is, but I'm going to show you the trick. That means that x of t here is equal to the summation from n equals minus infinity to infinity of some C of n e to the j n omega naught t. And here I'm going to also say something. C0 will be equal to 1 over t, the integral of x of t dt from, I'm just going to go from 0 to t on this one. And C of n here would be equal to 1 over t, the integral from, say, I'm going to go ahead and say from 0 to t, it's over any period of x of t times e to the minus j n omega naught t dt. So I wrote all that down, and all this pertains to this particular functional form. Are you with me?
What's in on the first line? It's negative infinity to what?
Yeah, it goes to infinity.
To infinity.
Yeah, it's over, yeah, but I just put C0 down, I break C0 out, but you don't use an integration. C0 is just the average value, so you always break that out separately, all right? Remember that, what I'm telling you. Now, when I have this, I'm going to take a derivative with respect to time of this and work with numbers. So if I take a derivative with respect to time, and this is now my x prime of t here, what happens? Well, I come from 0 and I go to a. What's that derivative called, people? A delta function with a weight of a in front of it because it went up to a, it didn't go to 1. So this becomes simply an arrow here, a. That arrow indicates a delta function. Are you with me? Now, it keeps going until I hit tau. And when I hit tau, right, now it goes down to what? Minus a, right? And then over here at t, goes back up to a. And over here at t plus tau, it comes down to minus a, and so forth. Right? Now that's x prime. Now I come over here, right? And I said, that's x of t, right? Now I'm going to take a derivative with respect to time on x of t. And I say that x prime of t is equal to still summation from n equals minus infinity to infinity of C of n. But what happens when I take a derivative of e to the j n omega naught t?
You get 1 over j.
Derivative, not integral.
Oh, sorry.
Brings out the j n omega naught, correct? So now I get C of n times j n omega naught here, times e to the j n omega naught t. Do y'all see that? Now, do you notice that C of n times j n omega naught looks like a single constant, doesn't it? I mean, for a given value of n, it has a singular value. Do you agree with me? So I can say what that really looks like here is this. It looks like the summation of some C of n prime, e to the j n omega naught t, n goes from minus infinity to infinity, where C of n prime is equal to 1 over t, the integral, can go from 0 to t of x prime of t e to the minus j n omega naught t, and also C of n prime is equal to C of n times j n omega naught. Now, I'll let you write that down. I'll tell you why I'm doing what I'm doing. All right? And furthermore, I can say, therefore, C of n is equal to C of n prime over j n omega naught. You'll see why I did it. Just write it down and listen. You're going to get something out of this. Believe me, you will thank me in the courses to come for this one. This is a gift. They don't teach this normally in this course, but it's probably the most valuable trick that you can have with Fourier series analysis. All right? Now, here's why I did that. Y'all see I have delta functions, right? I took the first function and I took a derivative until I had delta functions. Follow? Now, delta functions are very interesting because if I integrate, like what am I after here? I'm after the value of C of n prime, right? Just watch this. C of n prime here is equal to 1 over the period times the integral of the weight is A, right? Times delta of t minus delta of t minus tau times e to the minus j n omega naught t dt. And we can start at something just below, I'm going to say minus, I don't know, t over, no, let me just go this way. It's going to be something, say from minus t over 4 to 3/4 t. What I want to do is integrate, but I don't want to go through, I don't want to start here, all right, and in here. This would be a tough integration. I'm going to move the window through here so I clearly have only 2 of these things to work. All right, with me? Because it can be over anything of a width period, 1 period. So I'm going to start right there. Follow me, class? Just before the first one starts. Give me that, guys? Now, why are these delta functions so valuable? What is C of n prime? Just look at that. It's 1 over t times a, right? But what happens? When a delta function turns on, right? What do we do to get the value of delta t times any function, f of t dt? Anyone? You evaluate the function where the delta function turns on. It turns on at t equals what? Class? 0, right? We evaluate e to the minus j n omega naught times 0, right? What is e to the 0? 1. It's 1. So the first one, a delta t times that, you get a 1 out of it when you do the integral. Are you with me? That's delta t times this dt integrating through. What about the second function? Where does it turn on? Can you all see this? Tau, right? So what do we get? We get e to the minus j n omega naught tau with a minus sign in front of it. I took the a out in front. So I get minus e to the minus j n omega naught times tau here. That's C of n prime. Do you all see that? Those integrals are no-brainers. The only thing you do is look at whatever it is that delta t is multiplying. It's called the kernel of integration. What's next to it? That's this. Evaluate it where the delta function turns on. Pull the value out in front. Are you with me? Now the a is a scale factor. That goes out in front, right? Are you with me on this? Now, I got that C of n prime. How do I get C of n? I simply do what?
divided by
J n omega naught. That's right. I take this, which is a over t, right? And I have 1 minus e to the minus j n omega naught tau here, and I divide it by j n omega naught. Are you with me, class? That's C of n. That was pretty easy, wasn't it? How many agree with that? Beats the heck out of integration. Listen, that one's not an integration by parts per se, but it is an integration. This is a trivial way to get that information by doing what's called the derivative method. Are you with me? I've got to form this into something that's a little more recognizable in a second. Write that down. I'm going to tell you this. What engineers try to do is create functions that they can visualize in their mind easily. I look at that right there. I don't know what it is. I don't. I mean, maybe somebody's much better at this than me, but I can't tell you what that looks like just by looking at it. But here's one thing I can do. I can take this right here, turn it into something that is more recognizable. That comes over here. Now, I don't know, frankly, I think you do. Y'all know what a sine function looks like, right? Do you know what a sinc function looks like? How many have heard of sinc functions? Sinc functions are really a sine of x divided by x. So it's a sine wave, only the amplitude is going down as 1 over x. Right? And I'll get you that. This looks like a sinc function. Let me show you what happens. First, I'm going to go ahead and I'm going to factor out of this. 1 minus e to the, I'm going to put this as this. I'm going to take a over j n. Omega naught is really 2 pi over t, isn't it, class? So times t is just 2 pi. So I'm going to take those out of there. Then what I'm going to do, the 1 minus e to the minus j n omega naught t, I'm going to factor out an e to the minus j n omega naught tau over 2, I should say tau. So I'm going to take e to the minus j n omega naught tau over 2 in front. That leaves me with e to the j n omega naught tau over 2 here, minus e to the minus j n omega naught tau over 2 here. You all see that? All right, what's this times this? This times this would be e to the minus a times e to the a is, you add exponents. E to the a minus a is what? E to the 0 or 1. Isn't that a 1 there? All right, that's what I did. Well, really the reason I did it, why I factored that out, does anybody see what this might look like? Take a gander. What identity we're using? Euler's, right? I want to put it up again. Remember this, guys, you're engineers. Sine of theta is e to the j theta minus e to the minus j theta over 2j. Y'all remember that? Do not forget that. You will use these all during your engineering career. You have to. Unless you're in sales. I always have to say that, because I've had somebody call me. I don't ever use it. Really? What do you do? I'm in sales. Oh, 10 more washes I should. But it's a true story. I'm not joking about this. This is an engineer selling stuff. Not washers per se, but a lot of stuff. All right, everybody follow me on this, guys? Now, what does this look like? What is the equivalent to the theta here? N omega naught tau over 2. Isn't it, class? Can you all see that? So now what I'm going to do is take this, I'll put it over here. And that's equal to A over J. I'm going to go ahead and I'm going to leave it as, I'll put the T in here. I'm going to go back that way to the, and then I'll put the N omega naught for a reason. I'll tell you in a second. And I'm going to replace this by what? J times 2 times sine of N omega naught tau over 2. Follow me on this? I've got it. Because if you take 2j on this side, then you have basically this, don't you? Can you all see this there? Everybody, by the way, if you didn't get your paper, you're coming in late? No. I don't know where it is. It's one of these. Yeah, it's down here. You'll get it, won't you? Can you all read this here?
No.
You can't? All right, I'll put it over here. I'll write it. Let me go ahead and erase this and put it here. Sorry about that. I'm gonna try to write the big too. Here's what I started with. That first part was A, right, over J times T times N omega naught. I'm gonna leave it like that. And then what I did is I have 1 minus e to the minus J N omega naught tau here, right? And then that was over, that's J N omega naught. Yeah, that's it, right? So what I did is I factored this, and then I had A over J times N omega naught T here. And then I had e to the minus J N omega naught tau over 2 times e to the J N omega naught tau over 2 minus e to the minus J N omega naught tau over 2 here. And that came down to A over J N omega naught tau, right here, times e to the minus J N omega naught tau over 2 times, and that becomes 2 times J times the sine of N omega naught tau over 2. Go with me? Yeah.
Is that A over J in 2 pi?
Yeah, but you can put it that way too, because what is omega naught? 2 pi over t, is it? 2 pi over t times t is just 2 pi.
Okay.
But I wanted to bring it back this way for a reason. Okay, I'll show you this. Can you all see that? How many do? Now this you understand, don't you? Sine of something? Sine of n omega naught tau over 2. Just use the whole n omega naught tau over 2 and graph that on one axis. You know what a sine wave looks like, don't you? Now the values of n means that this will just take discrete values with the envelope of the sine, right? But downstairs you have n omega naught t, right? Well, the n omega naught t effectively, as n gets larger and larger, the values are going to go down. So it's a damped sinusoid. Now let me show you what a sinc function is and why we're going to turn this into a sinc. I need to erase that part of the board, and then we'll get back to the derivative. This is really powerful, really useful. In a way, I'm glad I didn't give you problems that caused you to have headaches doing integration. I know you have calculators that do this, but some of these integrals, the expansion or the result is so long and it's tedious to evaluate. I suppose you could put hard limits in, but you don't know, they're really like from 0 to t. I'm not sure how your calculators stomach that. Here's what I'm going to do before I start messing with this. I'm going to introduce you to something called a sinc function. Write this down. SINC of x. Well, that's equal to the sine of x over x. That's all it is. Now I'm going to put a caveat here. That's the definition of sinc function in our book. However, in most modern electrical engineering books, most, that teach signals and systems or do radar or EMC or I can't think anything else just about, use this definition. We do not. The sinc of x is equal to the sine of pi x over pi x. And I'll tell you why they use this definition. Because if you graph this function, the top one, I'll call this A right here. If you graph sinc right here of x, right here, sine x over x, well, it starts at a value of 1, all right? Then it will go to 0 when the sine is 0. When's besides sine of 0, when's the next 0 in the sine function? Starts at 0, right? Pi over 2 is 90, or it's pi over 2, it's 1, right? What happens at pi? 0. That's the first 0 that's not at 0. So at pi it goes to 0. Where's the next 0?
2 pi.
That's right, 2 pi. But it's damping, it's doing this. And it's going down. You see this? This is going to asymptotically decrease as 1 over the value on the horizontal axis, if this is x. That's what the sinc function looks like. It's an even function as well.
Shouldn't it go to infinity, or never mind, the limits?
You have to do, when you take, to get the actual value at 0, right here,
Yeah,
take the derivative from top and bottom, you get a cosine, right?
yeah.
Over 1, cosine of 0 is 1. Right, L'Hopital's rule, remember, derivative top, derivative bottom. Evaluate it where the function has a singularity. Understand, class? So here, that's the sinc function. It just keeps us a dying sine wave. We use this all the time. But that's something I can visualize easily. Do y'all agree with that? But here's why they do it this way in most books, and for most purposes. It's really, it's a thing, anybody that really works with this, they don't like looking at pi's and 2 pi's. They would like 1s and 2s and 3s. All right, we'll graph that function. At 0, the value is 1, all right? The sine of pi x over pi x. Where's the first 0 after 0? When what? X is 1, follow me? So if this is x here, at 1 it's 0. And the reason this is so nice, the next one's a 2, and so forth. And so people use this definition for one and only one reason. To display it is much easier, and to understand it, it's much easier. You're not dealing with those pi's, that 3.1415, all that crap all the time. It's like 1, 2, 3, and it's much easier to deal with when you're trying to manage a filter design later on. You'll see this. But we don't use this one. We use the top one, which brings me to my next topic. Back to this guy right here. With me? Please watch this. Now you all see the J's can be erased top and bottom? There's a J here, there's a J here, right? We just get rid of those. They're a nuisance. So get rid of them. Now, I know for a sinc, I need sine of x over x. Can you see x is n omega naught tau over 2 here? Do you all see that, class? So I got a sine, so I need to divide it by n omega naught tau over 2, right? Here's my n omega naught. That t doesn't do me anything. Now I need a tau. So I put a tau on top, and I put a tau on bottom. Follow me? Now I need a 2 downstairs. I need to divide that by 2. And there's a 2, right? Divide top and bottom by 2. And now I get this. Don't I, class? Y'all see that? It's very simple. So now I have sine of n omega naught tau over 2 divided by n omega naught tau over 2 times a tau over t. So I'm going to write it. So now I can say my C of n here is equal to a over t times tau. Better yet, let me do it this way. A weight, times tau over 2 times e to the minus j n omega naught tau over 2. And then it's going to be times SINC of n omega naught tau over 2. Are you with me? Now that's a little more recognizable. All this is just a magnitude, a tau over t, pardon, not 2. This should be t. A is just a magnitude, correct? Like 5, 10. Tau over 2 has a unique term. We used to define it for a square wave. Do you remember what it is? What is the ratio of the on time to total time of any kind of a clock cycle? Duty cycle. Do you remember that? How many do? Remember duty cycle from, did y'all have your digital course yet? Yeah. Did you? Who had digital? Well, either one, digital electronics or digital logic. Did you have digital logic?
Yeah.
Well, digital logic, remember clock cycles? And they took the on time, off time, that was called the duty cycle? What do they call it? No, the clock. What if the on time is only 1/10 of the entire time? That's called a chirp waveform. You didn't have this yet, this comes later. A chirp waveform and stuff like this, but the ratio of on to total time is called a duty cycle. And that's what this tau over t is. We'll get to that later. You'll be using this extensively in your engineering course. This e to the minus j and omega naught tau over 2 is really a phase, is it? That's a phase. E to the j anything has a magnitude of 1. So when you take a look at the magnitude of C of n, what you're really talking about is something where you have a constant a tau over t times a sync waveform, right? And the magnitude of the sync waveform looks like this. It's just the same as that. Only it does this. It's strict positive. Follow it? That would be the magnitude of C of n. That's pretty easy to see, isn't it, class? Now, when you take the values of n omega naught tau over 2, what you're doing is extracting values at these points. This would be like n equals 1, 2, and these would be the values of that C of n. It's very interesting. See what I'm talking about? But that's visual. You can visualize that, can't you? It's easy to visualize. The first part wasn't at all. And that's something you're going to see over and over again, the sync function. Remember that. This is your first exposure. Over and over and over because it's easy to see. Easy to see. And usually what we plot is not the magnitude of C of n, but it's magnitude of C of n squared, because C of n squared is power at a given frequency. It tells you how much power is at a given frequency. And when you're doing any kind of analysis in the frequency domain, you look for the amount of power at given frequencies. This is especially true when you're doing Wi-Fi work or radar work. You want to see how much power is at a certain frequency over a certain band, too. That's real important. So that's your first exposure to this. Now, more to come. So we're going to do another one using the technique. It's the derivative technique. Here's the game of this one. We're going to do this one. It's a little more complicated. We're going to do now we're going to do something where it's going to take a couple of derivatives to get down to the actual impulses. We're actually going to break it up into two functions. Write this down. This is a real good one. Here's the actual thing we're looking at. And you will see be able to extrapolate to any type of functional form. So this is t. And the waveform I'm going to have is this. It's going to go up at tau to a value of a. It's going to stay there until I hit, let me call this tau rise, and then call this tau. Then it's going to go straight down to 0. And it's going to stay that way until I hit t, and then the thing's going to repeat. And just keep going. Does everybody see this, class? And this is my x of t. Are you with me? Now that x of t, remember, is represented as a summation of c of n e to the j n omega naught t, n equals minus infinity to infinity, right? And here is, actually, just under that. The value of c of n for this one would be 1 over t times the integral from 0 to t of x of t e to the minus j n omega naught t dt. And c0, always get c0 from the actual function right there. c0 would just be 1 over the period, the integral from 0 to t of x of t dt. Just by looking at this one, can you tell me what it is? Well, it's really going to be the area under this thing divided by the period t, isn't it, class? Is that right? So what's the area under that? C0 would be 1 over t, and the area would be, think about this. It's going to have Well, it's going to be A times what? Times tau minus tau rise for starters, right? So I got A times tau minus tau rise. I know I have that much. Plus, then I have what?
1/2.
1/2 this area. So 1/2 times A times tau rise, right? Or it's plus 1/2 tau rise. So we can get the constant C0 right off the bat. Pretty straightforward. Just area under the curve divided by period. Follow me, class? Now, I'm going to take a derivative of this one. Again, I wrote those things up there for your edification. And when I get a derivative of this, let me get up a little higher. I want to make sure you see this. When I take a derivative of that, what happens? Well, how about between 0 and tau rise? What do I get? Class?
Yeah.
I'm going to get something with what? A over tau rise is the slope, correct? It stays there. What happens when I hit tau rise? It's 0, right? The slope of that line is 0. It stays there until I hit, say it,
Tau.
tau, right? And when I hit tau, what happens?
You get a negative delta function.
And with a weight of?
A.
Does everybody see it's weighted by A in front there? I use the word weight because that's common in engineering. People always say you weigh something or you multiply it by that. It gives it, that's how much of an effect it has. So this becomes minus A. And then this would repeat itself. So here you would get this again. And so forth. You all see that? Right? Sorry. This would go to there, and then it would stay there until I hit here, and then I would get this. Now, if you look at this carefully, what you see is something where I have a series of just delta functions, don't I? You all see how we would have just delta functions that are negative that would occur at what? Tau, at tau plus t, at tau plus 2t, and so forth. How many see that? That's solely delta functions, but I also have this function, right? And that's a square wave. So what I do is create two functions. I'm going to say that this first function, just this square well that repeats itself, I'm going to label that x2 prime of t. And I'm going to say xt is really going to be made up, no, I'll call it x1. It's going to be made up of x1 of t plus x2 of t. So there's two functions. And this is completely legitimate. I can get two Fourier coefficients. Take a derivative of that. Now the first one is not delta functions. It's just going to be this series, the repetitive square well. Do you all see that? The second one is going to be this. I'm going to say this is x2 prime of t because there's a derivative. Are you with me? How many see this right here? Straightforward, right? I can take that derivative. What I'm going to do is say it's really two functions. The ones that are just delta functions, which I want, I'll call x2 prime. And the one that's the square well, I'll call x1 prime, right? You all see that? Now here's my game. Can I go ahead and get the cn2 prime for that one? Yes, right. Because it's deltas, correct? So now I'm going to come over here, all right, and I'm going to say my x2 prime of t can be represented as some summation, right, of cn2 prime times e to the j n omega naught t, n equals minus infinity to infinity, and that's simply equal to the summation of cn2 from n equals minus infinity to infinity times jn omega naught times e to the jn omega naught t. And let me even go a step further and say each one of these has their own Fourier series, so this is equal to a summation n equals minus infinity to infinity of, first one would be what? Just cn1, then it's plus cn2 times e to the jn omega naught t. I can take that And that should make sense there, but does everybody see I just wrote the summation once instead of twice? I put the CN coefficients as additives in there. How many see this, class? All right. Can you all see in the back? You guys that sit in the back, I don't know how you can see. I've been back, but I don't know how you see. All right, now why is this only, remember, when I did take one derivative of that, you see there's only J and omega naught that comes out of it? With one derivative, right? Are you with me? How many follow me on this one? You got a lot of weird looks, like I hate you. I'm not feeling anything good here right now. So I can go ahead and get this Cn2 prime because this is in the form of a Fourier series. It's a coefficient times an exponential, right? So I can say my Cn2 prime will be 1 over the period times the integral of my x2 prime. It's over there. Anybody know?
Very well, people.
Verticality.
What's going on? You know, of course.
It's a chemical engineering course.
All right, now watch this. What is x2 of prime? There's one derivative in a period. You all see that? Integration over any period, just one derivative. Do you all see this, class? How do we represent that? We could represent this, if you wanted to, as minus a delta of what? T minus tau, correct? Are you with me? You all agree with that? Let me show my hands, how many do? So what happens when I stick that in here? What do? It turns on at what time? T equals?
Tau.
Tau, it's got a minus a weight in front of it. So I can put minus a here, right? And then what do? Evaluate e to the minus j and omega naught tau, right? Because that's what it turns on. So it's just e to the minus j and omega naught tau. And that's my Cn2 prime. Got it? How many see that? You look thrilled.
I'm just trying to keep up.
I'm trying to be really, I'm not trying to go fast here. I'm trying to make you see this. Are you with me? You might get tired of writing this J and omega that stuff, but as long as you see the essence of what's going on, it's very straightforward, very simple. Now, that's a prime though. Now to get the actual value, don't I have to divide that by J and omega naught? Because this right here is the same thing as that right there, correct? And I'd solve for my Cn2 prime. So then I just divide that by J and omega naught, and now I can say that this this Cn2 right here that I'm after, keep this thing on, will just be equal to that, divided by J and omega naught. So Cn2 will be equal to minus a over t, J and omega naught, times simply e to the minus j and omega naught tau. That's Cn2. Are you with me? How many see this? We got one of them, right? Now we need to get the coefficient associated with this x1 prime. Are you with me, class? Now remember, this x1 prime is really what? Cn1 times e to the j and omega naught, right? We take one derivative of that, then x1 prime, therefore, would be equal to Cn1 j and omega naught times e to the j and omega naught t, sum from minus infinity to plus infinity. And then we take another derivative, and we're going to get j and omega naught squared. Now, here's what I'm going to do, class. Can you allow me to erase those x2 primes there, just so I can focus on x1 prime? Are you okay? Because I only got one board here, and I don't want to do too much. So this guy's done. We've already figured out what that coefficient is. Now we've got this left, right? Square root. It's a square root, isn't it, class? What am I going to do to get deltas? Make a derivative with respect to time. Am I not, class? And when I do, what do I get? Now we're going to take another derivative with respect to time. And now I get x1 double prime of t. And what happens there? Anybody?
Positive delta at 0.
Now I get a delta function here, right? And the weight of that would be what? A over tau rise. Correct, class? Can everybody see this in the back? Keep going. Where does the next thing happen?
And tau rise, you get a negative delta A.
Minus, correct? It goes from A over tau rise down to 0, and now I get this. Minus A over tau rise, and this occurs at tau rise. Now I've got two delta functions, don't I, class? Do y'all see that? I could write the first one here as what? Just A over tau rise times delta of t, correct? And what about this one? How could I express this mathematically? Minus A over tau rise times, class? Delta
Of tau rise.
delta of t minus tau rise.
Oh, sorry, I was
Delta
saying right.
of t minus tau rise. Are you with me? That would be that function. Do you agree, class? Are you with me? All right. Make sure you're on top of this, because this stuff gets confusing if you don't stay with it. It really gets confusing in another 2 or 3 lectures. But this stuff you have to stay up with. This is engineering. Engineering is not for the faint of heart. It's not for the people that are used to just skating. I mean, this stuff is hard. It takes a lot of time. If you're not committed, you'll probably fail. It's just that simple. You got to be bright, hardworking, and more than anything, just intensely serious about doing this, because this stuff can kill you. So now I've got a delta function here, delta function here. Do you all see that this is going to repeat itself? Up and then down. Up, down, up, down. Do you all see that? Just delta function. Now we have all delta functions, don't we? Now we have x double prime t. Now what is x double prime t? I'm going to go ahead and erase this part. How about I do it right in the midboard here? So now I've got my CN2 right there. Now when I take a look at this, when I get my x1 double prime of t, that was equal to the summation n equals minus infinity to infinity, and then we would have jn omega naught squared times cn1 times e to the jn omega naught t here, right? Which can be rendered as x1 double prime of t times the summation of cn1 double prime e to the j, bless you, n omega naught t, n equals minus infinity to infinity. Do you all agree with that? When you take two derivatives, you get a jn omega naught squared in front, agree, class? Times c of n. Now look here, just listen to me. They'll be in to get rid of us in a second. Isn't this equated to this? You agree with that? Right. So how do I get my CN1 double prime? Well, my CN1 double prime will be equal to 1 over the period. The whole purpose of this is getting things in terms of delta function, so the integration is trivial. That's the idea. Then when I get the double prime, I just divide by the number of jn omega naught to the n, where n's the number of derivatives I took to get there in time. It's that times the integral, and in this case I'm going to go from just a little bit below to t minus epsilon of that right there, which is minus a, right, over tau rise times delta of t minus delta of t minus tau rise times e to the minus j and omega naught t. I'm going to finish this thought. And therefore, what does this become? Cn1 double prime is really what? A over t tau rise, right? Put a minus sign there. I get 1 minus e to the minus j and omega naught tau rise. And then you would divide this by j and omega naught squared. Divide by j and omega naught squared to get cn1. And that would go, let me just cn1, that would go right there. And now we have solved that without ever doing an integration by parts and cursing. I know what I'm talking about. I used to have to do this. I remember when I was where you were. I would get integration by parts usually twice for a lot of these coefficients. They would be nasties. And sometimes it would be more than that. Did you have a question? Nobody? All right, I'm gonna give you homework on this, make sure you do it. The question you have for me is, what's on the quiz Friday, right? It'll probably be a simple thing related to this. All right? Go to my office, I'm gonna figure it out. Tomorrow, I teach from 9:30 to 10:45. How about from 12? Let me ask you this. I'm really sensing a lot of resistance to this stuff. All right, I'll give you a quiz on operational amplifiers and Laplace, but if I may, if I sense that you guys didn't do a thing, this quiz is coming at the end of class, I may put a part of that on that. All right, something. So I want you to do this homework. All right, got me on it? If I sense you guys didn't do this homework, I'm gonna give you a quiz on that.
Why is that negative A over tau R?